Welcome to welcome to the fifth lecture from chapter number 4. We are studying fabrication of CMOS ICs, and in this lecture we will study a technique that is used to form different layers on a given silicon chip, mostly mostly doped silicon layers or CVT based oxide layers, etc. We already know that an IC is a three-dimensional set of patterned layers. They are not in two dimensions, but they are in three dimensions, and all turns are on 90 degrees. Submicron features on the level features at the level of micrometers are obtained using a process we called photolithography or just lithography. The process is similar to fabrication of a CMOS, fabrication of a PCB printed circuit boards, which electrical engineers or electronic engineers usually start learning in the start of their BSc engineering. But the difference that the resolution of this manufacturing is very small. It's almost of the order of zero point 0.1 micrometer. So this is a very fine process, or you can think of it a very fine PCB manufacturing technique. The process can be divided into which process? The process of lithography or photolithography can be divided into various parts. The first step is to make a mask or reticle that we usually do in PCB manufacturing. The size of reticle, that is, the reticle contains two portions, transparent portions, this one, and opaque portion, for example, this one, right? So size of reticle is 5 to 10 times greater than the size of the actual chip on which we are going to translate this pattern. So first we make this reticle or mask, and then we coat the silicon wafer. This is silicon wafer with a material. We called it silicon wafer. We coat it with a material we call it photoresist. It's a specialized material, and then the material is of course sensitive to light, and then in step number 3 it is exposed to UV light, ultraviolet light, and the ultraviolet light is projected so that we can have a smaller pattern on the IC chip compared to the reticle we have prepared. So this is reticle that is 5 to 10 times greater than the actual IC on which we want to translate its shadow. Right, so we put it under a UV directed UV light, or projected or directed UV light, and light is passed through the light passes through these transparent portions, and of course light cannot pass through these opaque portions. So on actual silicon chip that is beneath this one, the actual silicon chips, there are portions which are exposed to UV light. The portions that are under this transparent parts, and the portions which are under these opaque parts are not exposed to UV light. That is the difference we want. And then the next step is rinsing. Chemical rinsing step includes the portions that are shielded that are under the opaque portions of the reticle or mask, they are hardened. They're not soft, but the portions that are exposed to UV light are rinsed away, can be rinsed away. In fact, these portions which are transparent, they are not hard. The opaque portions, the portions that are opaque are hard. So in the next step, we make a difference. We have a difference between the portions that were exposed to UV light and the portions that were not exposed to UV light due to being under these opaque portions. So let's see what is the difference then and how differently they behave, right? This is a cross section of the reticle or mask that we have used here. This is a cross section of the mask, and we see that at some portions this is opaque, for example this portion and this portion, and for certain other portions this is transparent. So UV light passes through transparent portions and it falls on the wafer which has already been coated using the photoresist material, right? The portions that are under the opaque portion are hardened like I have shown you them here, but the portions that are not under the that are under the transparent portion or which have been exposed to UV light are softened and can be rinsed away using using different chemical. So, etching process doesn't work under hardened hardened layers. The chemical etching process that is used to remove the portion from that can be used to remove the portion from these from the portions that were under the UV light. They that etching process doesn't work on that etching process doesn't work on hardened layers. The layers that were hardened the layer that was under the opaque portions and it was not exposed to UV light, right? And then we have the second last step, that is etching. This process removes patterned layers using inert gas. Inert gas is a gas in periodic table. We have many such gases in periodic table which are having full 8 electrons in their outermost shell, and they are inert, means they do not react with any other atoms, right? And for example, argon. There are many gases in the same last column, eighth column of the periodic table. In that column of the periodic table, for which we have 8 electrons in their outermost shell, and they do not react with any other metals or materials. The process is called reactive ion etch, RIE. For example, if we want to make a pattern of this underlying material, where on top of P substrate we already have a silicon dioxide layer, and we need to pattern it like this, that for certain portions we want to remove this layer, even the silicon dioxide layer. So this patterning is carried out using RIE, reactive ion etch technique. The same technique that we harden some layers by applying reticle or mask over it, which is opaque at some portions, transparent and at other portions, and then it's exposed to UV light, and some portions are hardened, some portions are not, and then we can apply these chemicals, rinsing chemicals to rinse this whole part out, and we keep this. And with the use of certain other materials, we can remove these hardened layers so that we have only this patterned silicon dioxide layer on top of this substrate. Finally, we can implement or convert part of these into doped silicon layers. For example, you want to implement an n plus here, n plus here, or an n plus here. So how can we do that? We can do that by using the technique we call ion implantation technique we studied in last lecture. We will bombard arsenic or antimony ions which are pentavalent in nature, pentavalent impurity. So these are pentavalent impurity ions bombarded on top of this material, and and they cannot pass through these hardened layers. They only pass through these exposed portions and etch these portions like this, n plus and n plus. So this is before, and this is after we have done it. Right, we will continue studying in our upcoming lectures more techniques related to fabrication of CMOS ICs. Thank you.